Welcome back. So, today we are now going to be start the next phase, and in the next slot whatever we are going to discuss is about the modeling of multi-phase flow reactors. We have already discussed some of those modeling parts during the previous phase and during the discussion of the pressure drop, and once we have written the equation into a one dimensional domain. Now, what we are going to do? We are going to see the three dimensional modeling. So, till now whatever we are discussing the equation, and most of the thing our discussion we have limited ourselves in the one dimensional domain. Now, we will move towards the three dimensional domain, and we will see that in the three dimensional domain how the equation will be modified and how to solve those problems. For second thing, we were not talking about the much interactions till now. Now, we will see that different type of coupling and different interactions and how to incorporate those interactions, so that we can do the simulation or modeling for the industrial scale equipment. So, to begin with, what I will do, I will just revise some of the fundamentals, so that you again actually come to the same level and we understand that what is the need in the modeling and why we do the modeling of any multi-phase flow reactor or any modeling at all. So, whatever we have discussed till now, the phenomena which affect the multi-phase flow reactor performance, whether it is a discrete or it is a continuous, this first phase or it is a continuous phase, is actually the flow dynamics of the multi-phase dispersion. So, how the flow dynamics is being involved, that is what it affects. And once we say the flow dynamics, what we mean is that the fluid hold up, the hold up distribution, it means what is the hold up or phase fraction or volume fraction of a particular species or particular phase, and how it has been distributed. Then we mean about the fluid and particle surface or interfacial areas, that how they are, what is their surface area and what is the interfacial area in between them, the size of the bubble, catalyst size distribution, and all those particle size distribution which we have discussed, that how they are changing. Then how the mixing is taking place. Now, mixing can be get from the RTD. Okay. So, how this mixing is being taken place or will take place. Then we want to understand that how the bubbles, if suppose there is a bubble column, then what happens? We said that as a single bubble which is moving up. Now, we can talk about that how the multiple bubbles are moving up, how their coalescence or breaking are taking place, how the catalyst particles are moving together, will have some attrition and agglomeration. We need the information for that. We need the information from the heat transfer phenomena like liquid evaporation, condensation or fluid to wall interactions and all. We need to find that. And then how the energy is being dissipating. Okay. Now, this energy dissipation can take place from the various sources, like if you put a stirrer, that will be there, the fluid interactions, the viscous forces, all those things will actually add to the energy dissipation. So, this is what we want to understand, and that combined package is called reactor model. Okay. And this reactor model is actually very critical, particularly once we are thinking about the scale up methodology. So, that is the main motivation of doing any reactor model, so that we are performing the experiments or we are understanding the system at one scale. We are doing the modeling, we are rigorously validating our model at that scale, and if I have done everything correct, if I have incorporated all these variables whatever we have discussed properly, then we will have a reactor model, and that reactor model can be used effectively to predict the performance of the reactor or behavior of the reactor for different operating parameters, and the same reactor model can be used to for the scale up studies or for the scale up of the reactor. So, that is the whole reason that why we go for the modeling and what is the need of the model. Now, as I said earlier that how the whole chemical process has been developed. So, we start with the basic chemistry, and that basic chemistry we develop at a flask scale. Then we move to the laboratory scale system. Now, in the laboratory scale system, what we do? We introduce the laboratory scale flow pattern. Then once we move from laboratory scale system to, if it gets success, we move laboratory scale system to pilot plant scale system. What will happen? This laboratory scale flow pattern will transform to the pilot plant scale flow pattern. Rest of the chemistry and interface transport remains same. If we get success further, we further move to the industrial scale system, and what happened? This pilot plant scale flow pattern is actually changed to industrial scale flow pattern, and chemistry and interface transport remains almost same. So, this flow patterns actually keep on changing, and we need to predict that flow pattern, and why it is still a challenge whatever we have discussed till now is the reason is that neither we have a measurement technique which can measure the flow performance or performance of the reactor with equal accuracy at all the level. So, that is the one major kind of a problem, Further, even to adding into that, forget about that, the accuracy remains same at all the scale. None of the technique is available till now, experimental measurement technique, which can give you all the parameters required for the scale up even at a laboratory scale. So, we need to build up on the experimental technique. Similarly, the models which we are going to discuss or whatever we have discussed earlier also in one dimensional, I have keep on telling that each model has certain limitation. So, that is true with the modeling part also, that we do not have even a computational model available or numerical model available, which is equally valid at all the scales, and that is the problem in the scale up strategies, that why we are not able to do the scale up properly, which is completely based on the science. So, to resolve that, we need to understand the limitation in the measurement techniques, the limitation in the modeling technique or numerical techniques, and we should use the appropriate model depending upon the requirement, and then we should, based on that model, we should scale up the reactor or predict the performance of the reactor, and we should know that what is the limitation. That is very critical to understand, that whatever the model I am using, what is the limitation of that model, how far this model is valid, how much accurate the model can predict the flow phenomena or predict the physics. So, that is what is the aim of this section, and we will try to see the different modeling approach. Some of them we have already discussed. Now, we will do some 3-dimensional modeling, we will do some rigorous interactions also, and how to solve the equations for the different phases or different domain, and we will try to discuss their advantage and disadvantage and limitation. So, that is the whole thing which we are going to discuss, and we will be mainly focusing in this section not on the experimental technique, but we will be mostly just focusing on the numerical simulation. So, what is modeling? So, computational modeling is nothing but is a method to represent a real world process by equation. Okay? So, that is what is modeling is. So, you see any phenomena, like if I am moving, you are seeing my movement, and if you write that movement in terms of the equation, that is called modeling. Okay? So, modeling is nothing but writing any physical phenomena in terms of the equation. Okay? And why we do the computational modeling? Because it helps us to analyze the physics, it helps us to understand the flow or understand the physics, and it can kind of prevent or it can kind of minimize the experimental measurements. So, you do not need to do the measurements all the time. Okay? So, if you have a fitted model, suppose if you are able to model my movement, you have to just do the measurements once. You have to fit a equation on the my movement, which will be model equation, which will predict my movement by behavior, and next time you do not need to do the modeling again. You can keep on predicting the motion, my motion all the time. Okay? So, that is the main reason that why we do the modeling, and main aim of the modeling you can say can be divided in these parts. The first aim is definitely the process synthesis, that a model can help me in the synthesis of the this process. Now, that model will be actually based on the molecular model. We can have a DFT simulation, we can have molecular simulation to see that how the two species will react each other. So, instead of performing the reaction, we can do some modeling. We can say that whether, say, if I take species A and species B, whether they are going to react or not. So, instead of doing the experiment, wasting money on the experiments, I can do the modeling. I can even predict a priori that okay, these are going to be react, and what will be the possible product or possible product distribution which will come out of these two reaction, or when the species A and species B will react with each other. So, it helps me a lot to analyze the process, to analyze the process synthesis, that how the process should take place. Then it also help us in retrofits. It means what? It helps us in troubleshooting. If you have some problem, you want to redesign, you want to improve that design, you want to correct some mistakes, whatever is being done either in the design or in the process conditions, you can do it with the retrofits, because we already have a model available. I can understand that okay, this model will be sensitive to this parameter, or if I change the design it in this way, how my model performance is going to change, and how not model performance, but how my reactor performance is going to be changed. So, if I have a model available, I do not need to do the experiments for all the troubleshooting. What I can do, if my model is well, if it is predicting well, I can do the retrofits. So, that is the typical use of the model and very critical use of the model to in the retrofits, so that we can do the improved troubleshooting, we can improve the existing equipment design and all, and even we can find the optimal parameters for which the reactor or the process vessel should be operated. Then R&D is a very critical part. We know that R&D is pretty much money governed, and you have to spend a lot of money. If you have to do the experiments for all the possible conditions, it will be very expensive. So, if you do the model fitting, you can minimize the cost of experiments, you can understand the physics, and that is very critical, because if I can write any process in terms of the equation only if I understand the physics of the process. Okay. So, if I understand the physics of the process, definitely my predictions will be much better, and I will also save on the money wise. So, I do not need to spend the money for all the experiments, I do not need to do the experiments for all the possible condition, all the possible sets, all the possible internals and all. So, I can do the experiments for certain sets, I can develop a computational model, and that computational model will help me to understand the physics of the reactor, and then I can analyze the performance of the reactor in presence of many other things. So, I can do it for one case, and then the other cases like without internal, with internal, for different velocity condition, for different pressure condition, my model can give me that how the performance of the reactor or process vessel is going to change. Then it can also help in improving the process. Okay. As I said that the process, you can analyze the process, you can understand the physics of the process. So, you can analyze the process and can improve the process, that if suppose some process, some say CSTR is there, where there is an impeller which is rotating inside, you are finding that your model is predicting that the mixing quality is not very good, the diameter of the CSTR vessel is very high compared to the impeller diameter. So, to improve the mixing, we can think about putting the baffles on the wall, and we can do our modeling with the model equation, and we can see the effect that whether if I put the baffles, whether it is going to affect positively in the mixing wise or not. So, all those process improvements. So, I can put the process, if it is improving, I can install the baffles. So, I have not done any experiments, was just with the modeling I can do this job. So, that is another very critical thing to improve the process performance. We can use the modeling, and definitely the equipment design and the scale up is one of the critical parameter that why we do the modeling. So, if you see that most of the equipment is being designed based on the model equation, those model equation which we developed based on the experimental data, or we fit the model equation and then we validate those model prediction with the experimental data, that model is being widely used for the equipment design. So, like for heat exchanger, we did the experiments few times, we fit some model equations, and that model equations are being used now, even till now, to design the heat exchanger. It is not like every time to design the heat exchanger you need to go and perform, make a setup, perform the experiment, measure the delta T, measure the flow rate, measure the pressure drop. You do not need to do all those things. Just with the model equation which has been developed, then you can do the heat exchanger designing. So, these are the major advantages that why we want to do the computational modeling, why we want to have a 3-dimensional model to understand the flow physics. So, what we have done till now, we have discussed about the interactions, but most of the interactions was actually we discussed in the one-way coupling or one-way interactions, like fluid motion is affecting the particle motion or particle motion is affecting the fluid motion, and we have developed the one-dimensional equation based on that. The rigorous interaction part we have neglected, but once we are going for the computational modeling or rigorous modeling, we cannot remove or we cannot neglect the interactions which are taking place between the different phases. Why? Because these interactions are the one who is going to govern the flow physics inside the vessel of interest. So, it is very important to have different interaction, and to have that interaction in your model equation, you should understand that what kind of a coupling take place between the different phases. Okay. So, there are mainly 4 type of coupling or 4 way of coupling. We call it one way coupling, 2 way coupling, 3 way coupling and 4 way coupling. Now, what is one way coupling and all? So, one way coupling means the fluid motion is actually affecting the particle motion and particle motion is not affecting the fluid motion, that is called one way coupling. Similarly, in 2 way, motion of fluid is affecting the motion of particle is affecting the motion of the fluid. So, you have to have a 2 way coupling. Now, if you are having a 2 way coupling, what you need to do? You have to include the drag in both the equation or both the phases. Similarly, we have 3-way coupling and 4-way coupling. So, to explain that, I will move to the next slide, and this is the slide where we can explain that what does the 1-way coupling, 2-way coupling, 3-way coupling and 4-way coupling means for. So, as I have discussed that for generally gas solid flow or any flow, any multiphase flow, we can divide in two parts. One is called dilute flow and one is called dense flow. Okay. Now, we can divide it as a dispersed phase flow and dense flow, and dispersed phase flow can further be divided as a dilute flow. So, what do you mean by the dilute flow? When the particle fractions are very small or discrete particle fraction is very small, the flow is called dilute flow, where the Stokes number is also less than 1. So, that is called dilute flow. If Stokes number is more than 1, your particle fraction is very high, then what will happen? The flow will be actually the dense flow. We have already defined that dilute flow and dense flow definition. You can just see that Stokes number is not the real place. We have already proved that when the flow will be dilute, when the flow will be turbulent. Whatever Stokes number I said is actually just a thumb rule, but there is a formula where we can use that, and we have already derived that formula from the dilute flow and dense flow conditions. So, in the dilute phase flow, roughly speaking, the particle fraction is very low, less than 5 to 10%. You can say that the flow is dilute, and in that case we generally use either the 1-way coupling or 2-way coupling. Now, 1-way coupling means what? The fluid motion or continuous phase motion is affecting the motion of the particle. Okay. So, that is called 1-way coupling, right. If suppose you have a particle rotation or particle rotated by the vortex. So, suppose if you go to river, you see some vortex formation or eddy formation. Now, that vortex formation, suppose this is the vortex formation which is taking place. If there is any particle in this domain, what will happen? The particle will also start moving it in this way. Okay. Once the particle will go to near to the vortex, it will also start moving it in this way, and it means what? The fluid motion is actually affecting the motion of the particle, and that is called 1-way coupling. The particle have no say in that. There is only single particle which is being stuck in a vortex. Then what will happen? The particle will start moving with the fluid, and that is means the fluid motion, particle motion has been started only because the fluid motion was there. So, it means only the fluid which is affecting the motion of the particle. So, in that way the equation we solve, we call 1-way coupling. Okay. So, what we do? We see the motion of the particle, how the motion of the particle will be taking place, will add 1-way coupling, and that 1-way coupling in this case is mostly from the drag. So, we use the drag equation, we solve the drag for the particle motion to see that how the particle motion is being affected with the fluid motion, while in fluid motion we do not include the drag factor. Then it comes to 2-way coupling. So, 2-way coupling is approximately same whatever it is there, but a solid motion is being affected by the fluid motion, and fluid motion is affected by the solid motion. Okay. So, that is why it is called 2-way coupling. So, now earlier what we said that there is eddy formation, a particle come within the eddy, it is start moving with the eddy or with the vortex, and the vortex flow or vortex motion is not being affected at all, while the particle motion is being affected and particle start moving in the vortex way, or it is start circulating. So, that is the 1-way coupling. In 2-way coupling, fluid motion is going to affect the motion of the particle, particle motion is going to affect the motion of the fluid. Okay. So, the best example for this is the wake formation behind the bubbles or the particle. So, suppose a particle is moving up and it is moving because of the gas velocity, a gas is being passed, there will be a wake formation behind the particle, and that you will see like something like this. And because of this wake formation, what will happen? The fluid motion will also get affected. So, this is called 2-way coupling. So, particle motion is affecting the motion of the fluid motion is affecting the motion of the particle. Okay. So, that is 2-way coupling, and it generally take place in the particle wake, where the increasing dissipation is there. So, where the particle wake is there, where the energy dissipation is very high, or it is keep on increasing, this 2-way coupling is very critical. Okay. So, that is for the 1-way and 2-way coupling. Both the coupling are critical for the dilute phase. So, once you have a dilute phase, you can have 1-way coupling or 2-way coupling. Generally, 1-way coupling and 2-way coupling is both is being governed by the drag force itself. So, in 1-way coupling, you solve the drag force in one phase. In 2-way coupling, you solve the drag force for both the phases. Okay. So, that is the difference in the model equation, and both are valid for the dilute phase flow. So, if you have a dilute flow, you can use only either one way coupling or two way coupling depending upon your situation. Then comes the three way coupling, and three way coupling says what? That whatever we have discussed, that the fluid motion affect the motion of the particle, particle motion affect the motion of the fluid. We also find that the fluid locally affects the another particle motion. Okay. So, it means what? Fluid is affecting the motion of the particle, particle is affecting the motion of the fluid, and fluid motion is not affecting the motion of one particle, but it is also affecting the motion of the other particles too. So, like if I take this case, okay, so the gas was passing up, particle start moving with a high velocity, it will form a wake. Okay. So, what happens, the once the wake has been formed, once the particle start moving, it means particle affect, fluid affect the particle motion. Then because of the particle motion, wake formation take place. So, this wake formation says that particle affect motion of the fluid. Okay. Motion of the fluid. Now, because of this wake formation, if suppose there is another particle which is somewhere here, what will happen? Because of this wake formation, the particle motion will further increase, and that means the particle motion, fluid affect the motion of the particle, particle affect the motion of the fluid, and then the fluid again affect the motion of the other particle. So, it is not affecting the only one particle, it is affecting the motion of this particle too, or this particle too, whichever is comes in the region of the wake. So, that is called three way coupling. Okay. So, that is called three way coupling. Three way coupling is being used when the solid fraction is keep on increasing or the particle dispersed fraction is keep on increasing. Three way coupling becomes important, because you have a wake formation, and in the wake the particle comes in. And we have already discussed a lift force during the discussion of the lift force. Suppose there is a bubble column where one gas bubble is being injected inside, and that gas bubble is actually moving, and because it is gas bubble and the shape of the gas bubble is generally in the mushroom shape, you can say that something of this kind of a wake formation will take place. Any bubble which will come in this range will actually go and have a coalescence with the previous bubble, because this velocity will keep on increasing, and because of that these two bubble will have a coalescence and they will form maybe a bigger bubble, or they may break into the two smaller bubble. So, in that cases where the wake formation is being taken place, it is very evident we use the three way coupling. Okay. So, four way coupling, then the next come to the four way coupling. Four way coupling means all three above whatever we have, we just say that the particle is also affecting the motion of the other particle. It means what? Fluid is affecting the motion of particle, particle is affecting motion of the fluid, fluid is affecting the motion of the other particles, and particles are affecting the motion of each other. So, that is called four way coupling. Now, we have all the four way coupling. The four way coupling, the fourth coupling is mainly because of the particle collision. So, suppose again the same example, if I have this for particle which is moving up in the air or in the because of the air and form a wake, okay, form a wake, and then you have a second particle which is actually been there, and that is actually motion is get affected because of this wake formation, and they goes and hit each other. Okay. So, they goes and hit each other. So, like this. So, what will happen now? This because of this interaction or because of this collision, the particle which was say earlier moving straight may start moving it in this direction. Okay. So, what will happen? The first particle movement, it means say this is first, this is second. The first particle movement have changed because of the collision of the previous particle or next particle which has been taken place. So, what it will be? It will going to affect the motion of the solids. So, what we are going to model is that the fluid is affecting the motion of the solid, solid is affecting motion of the fluid is affecting motion of the other solid too, and solid is affecting the motion of the solid. So, that is called four way coupling, all the four way coupling. In the dense phase, what we say that this is sometimes dominating based on the collision dominating. It means what? So, first four whatever we have discussed is actually present everywhere, but for the sake of simplicity, in dilute phase flow we know that the particles fractions are very small, they are very far from each other. So, the phenomenon are kind of the 3-way coupling and 4-way coupling. If it is there, it will be very low compared to 1-way coupling or 2-way coupling. So, that is the reason that for the dilute phase flow we remove the 3-way coupling and 4-way coupling, and we just consider 1-way coupling or 2-way coupling depending upon the application. While if you keep on increasing the solid fraction, you cannot neglect the collision, you cannot neglect that the fluid performance or fluid velocity is going to change the performance or the velocity or the characteristics of the next particle. So, that is the reason that we introduce the 3-way coupling, and when if it is further improved or further increase the fraction of the discrete phase in the fluid, you can say that now the 4-way coupling will be required, because everything is going to affect the motion of each other. So, that is the way the 4-way coupling is being done. In most of the cases, that is why we write it as a dispersed phase. Why? Because these couplings are important only if both the phases or one phase is at least dispersed. If both the phases are continuous, then these couplings are not that much relevant, okay, because they are not going to affect the motion of each other. So, they will affect, but not it in the great way. Say stratified flow, where gas is on the top, liquid is on the bottom. Okay. So, what is going to happen? If you do that, you are going to see that phase, then what will happen, that because this is a continuous phase, you are not going to change the things in that great way. So, what will happen, that because the flow is continuous, the interactions will take place only at the interface. So, they will affect, but they will affect only at the interface. Okay. And because there is only a clear cut interface, it is not possible that the motion of gas or motion of the fluid is going to affect the motion of the other phase, other particle, because only at the interface the fluid can be come into contact with each other. So, that is why all the 4-way coupling happen only if one of the phase is in the dispersed phase condition. Okay. For dilute phase, 1-way coupling or 2-way coupling is acting. For a very highly concentrated flow like a fluidized bed kind of a flow, the flow actually has been found to be collisional dominating. Okay. So, that is the kind, means that fluid is definitely going to affect the motion of the particle is going to affect the motion of the fluid, but the major problem is the collision between the particles is actually going to govern the physics of the bed, and that is the case once the volume fraction of the solid or discrete phase is very high, like in the fluidized bed which is just started fluidization, or you can say the fluidized bed operated at a minimum fluidization velocity or just above the minimum fluidization velocity, the flow actually will be pretty much collisional dominating, because there is not much movement of the solid. They started vibrating, but the bed expansion is very low. So, whenever they try to move, actually the particles try to move, it hit with other particle and then changes the direction, changes the motion. So, it is called a collisional dominating flow. Similarly, there are certain flows like settling, where the flow is contact dominating. Okay. So, it means what? The particles are being settled, how they are contacting with each other, that is going to affect the motion. So, that is called contact dominating flow, the one where the fluidized bed is there, which is being operated just above the minimum fluidization velocity, the flow is affected because of the collision. So, that is called collisional dominating flow. So, these are different coupling is there, and based on the application, as I said, we introduce the coupling, different type of coupling in our model equation. So, we should be very sure that what we are introducing, what is the purpose of this and why we are doing all this. So, that can be understood with this coupling equation or this coupling thing. Now, as the coupling is done, we need to solve the equations, and as I have already discussed that those equations are actually not complete. It means number of variable is more compared to the number of independent equation you are already having. So, what you need to do? You need to use some additional equation to solve the process or to solve your computational model. So, that can be done by using the closure problem. So, what we have already discussed that, this slide also we have discussed, I am again introducing it so that we can understand very clearly that in the model equation when we are using the other terms and what is the role of the terms. So, as we said earlier also that the gas mean motion or fluid mean motion is actually correlated with the fluid fluctuating motion, and that correlation is being modeled by using the different turbulent models. Now, you are free to use the any turbulence model whatever you feel like or whatever it is applicable. Now, I am not going in detail of that what is the turbulence models and different type of turbulence model, what is the limitation of each turbulent model and applicability of each turbulent model. So, let us assume that you understand about the turbulence model. So, depending upon the condition you can use a suitable turbulent model to model the interaction between the gas mean motion and gas fluctuating motion. And then it comes the interaction between the different phases. So, that interaction actually the interaction between the different phases like the gas mean motion or the fluid mean motion is going to affect the particle mean motion or dispersed phase mean motion, and that has been modeled by using a drag equation which we have already discussed. So, depending upon the condition again fluid we can use Seeler-Naumann, Morse-Alexander. If it is a fluid and solid, then we can use Gedaspo, Venn and Yu, all these correlations. Okay. So, based on the condition, the mean velocity of the gas and mean velocity of the particles are being actually related or can be correlated by using the drag. Then, because the particle is also moving or dispersed phase is also moving, what is going to happen if it is a solid? The dispersed phase mean motion or particle mean motion is going to be get affected by the particle fluctuating motion, and that the correlation between this or can be modeled by using the kinetic theory of the gases. We will discuss what is kinetic theory of gases. So, the mean motion between mean and fluctuating motion of the particles can be modeled by using KTGF or kinetic theory of granular forces, and the gas fluctuating velocity can be interact with the particle fluctuating velocity, and that interaction can be modeled by the energy of kinetic flux. Okay. So, these are the different closure equations available, and together with they actually close your equation. So, these are the different closure equations is available which you have to take care while modeling any process. So, what you need to do in the modeling, again I am telling you that what you need to do, you need to understand the process first. For that what you need to do, you can do kind of you can find that depending upon my process or depending upon my operating condition, what kind of a coupling I should incorporate, whether it should be one way coupling, whether it should be two way coupling, whether it should be three way coupling or four way coupling. Now, one can argue why I need to think this much, I can use all four way coupling all the time. The problem is if you are using four way coupling, you are solving the equations, more equations. Solving more equation is computationally expensive as well as it requires huge time without getting any additional benefits. So, if you do not say a very dilute flow, say for particle fraction is less than 1%, if you use collisional equation also, if you use that your three way coupling also, your collisional equation or four way coupling also, your two way coupling also, what will happen? You are increasing the number of equations which you need to solve simultaneously. So, you are increasing your computational time and the computational requirement. So, that is the reason we should understand that what are the forces which are critical, what are the closure equations which are critical, and how to use that closure equation, so that I can predict the motion of the particle or I can predict the behavior of the reactor with much accuracy. Okay. So, that is the reason why we want to understand all this. So, now what should be the approach? If you understand the system, what should be our approach, modeling approach? We call it multi-level modeling concept, okay? And that is the ultimate wish. That is why I said that ultimate wish is one day will come when I will not dependent on the experimental data at all. I will be doing everything through the model development. Like if I have to make a process, what I will do? I will first do the molecular simulation or DFT calculation to find that whether the experiment between the species A and species B will take place or not. Once I will able to do that, what I will do? I will take that equation, I will do the molecular level simulation by using the lattice-Boltzmann equation, that will be across one particle scale. So, what I did? First I did DFT kind of a simulation or molecular dynamic simulation, try to find it out if suppose I have to react species A and species B, under what condition the reaction will take place, whether I need the solid catalyst or not and all. So, once I have synthesized the process, I know my process requirement. Once suppose my process requirement says that I have to use a discrete phase reactor or say a gas solid reactor, then what I will do? I will first do the Lattice-Boltzmann simulation, though I am not going to discuss the Lattice-Boltzmann simulation in this course, it is a different scope altogether. You can read about it if you are interested. So, what I am going to do, I am going to solve the Lattice-Boltzmann equation to find the particle and fluid interaction, and that I will do across one particle or few particles. Okay. So, once I will develop that equation, what this equation will give me? This equation will give me a closure equation which will interact between the fluid and particle interactions, and that is nothing but the drag. So, I will get the drag equation from this place, that how much drag will act and how the drag equation should be there look like for this condition. Now, once I have a drag equation there, we will solve a discrete phase model equation. We will discuss what is discrete phase model equation. It is a Euler-Lagrangian approach that is called a mesoscopic scale. So, first one was the microscopic, because we are doing across one particle or one or two particles or few particles. Then we move to the mesoscopic bed. It means we are doing at a bed scale, but that bed scale is very, very small. So, say we are making a reactor with a very, very small size, say 10 centimeter or 10 mm or 2 centimeter or 3 centimeter in diameter, a very say 10 centimeter in the bed height, and we do the simulation here. We write the discrete phase model equation and we try to find it out the particle interaction phenomena. So, in this way I have developed the correlation for one way or two way coupling. Now, this will actually give me three way and four way coupling and or four way coupling. It will tell that whether the three way coupling or four way coupling is important or not, and what should be the correlation for that. And then we use in the continuum model, and the continuum model, as the name suggests, you are going to solve the Navier-Stokes equation. Again, I will discuss the equation, so do not worry about that, but the continuum model we will use, and we will now do the validation at the large scale. So, why we are doing it? Lattice-Boltzmann equations are computationally very, very expensive. So, that is why we are solving only across one particle. DEM simulation or DPM simulations are again computationally expensive, but not as of Lattice-Boltzmann equation. So, we have increased our scale. At a certain scale, we are trying to solve that interactions, and we are getting the interactions. And then we are moving towards the continuum model, where we are using all the equations or interaction closure which has been developed with this approach, and then we are solving at a large scale for the scale up for large scale reactors. Okay. So, that is the ultimate wish. Now, why that is a wish? Because right now we cannot do any of this simulation without having the experimental validation, because our numerical approach is not being matured enough. We still have lot of assumptions to solve those equations, and because of that, because you are using those assumptions, you need to validate your assumptions, and that is why the experimental validation is required. So, this is a dream. If I am working in the multi-phase flow, I always want to have a dream, or I always have a dream that I will do everything based on the model. I do not need to do the experiments, but right now the state of the art is not of that kind, and that is why the experimental approach is needed, and these links are not still well established, that how to use those equations in the other scale. Okay. So, that is what is our wish, ultimate wish, and we will come to this slide, that what is the different types of multi-phase flow models, approaches there, and how difficult or how easy they are. We will discuss it, but this is not the time. I think I will discuss it later on after discussing this. So, what we are going to do, the approach is to write the phenomena in terms of the model equation, and as we have already done, there are different type of model equations available, and depending upon the process conditions, the approach we are using, the accuracy required, the understanding required, we use different type of modeling approach. Okay. And depending upon the coupling also. So, there are different modeling approach, and what is that different modeling approach is actually, first is the empirical correlations, that is also a model. You perform the experiments, based on the you develop the data, kind of generate the data, based on the data analysis you fit some equation, and that is called empirically fitted equation and empirical correlations, and you use that correlation to predict the phenomenon, and that are widely used, this kind of a correlation for the single phase flow. Remember, any of your single phase flow reactor design, like heat exchanger or any other single phase flow reactor design, these all are based on the empirical correlations, okay, which has been developed by performing the experiments. We fit the equation, we develop some correlation and we use that. So, that is also a modeling approach. Okay. Differently, that empirical correlation even in multi-phase flow are widely used, like Locard-Martini correlation, which we have discussed, but there is a serious limitation of those empirical correlation. They are at least only valid for a particular range of the condition for which the experiments has been performed. Okay. So, that has been limited and the accuracy is being seriously limited to that range, and we have discussed that while discussing the Locard-Martini correlation, that it is just being used to get the first hand idea. Then we can use the Lagrangian track, the equation which we have solved in one dimensional domain. We are tracking the particle, okay. One particle, we are tracking just individual particles or one particles only, and we do not assume that the other particles are affecting the motion of each other. So, what we have done till now in the Lagrangian track, we can use that to find that we can use that approach to model the reactor performance, but the only thing is you can include only one way coupling or max to max two way coupling. Generally, we include only one way coupling. The way we have solved that there is a fluid, a particle is there in the fluid and the particle motion is get affected because of the fluid. We solve the fluid motion, particle motion by solving the Newton's second law of motion. We use the forces and the drag force becomes a very critical. So, you can use that Lagrangian track approach, but there is no way you can include the three way coupling. Two way coupling you can still think about, you can start solving the gas phase equation simultaneously both the equation and keep on updating, but we do not solve particle interactions in that case. So, that is why it is called Lagrangian track, it is relatively simpler. Then we go to algebraic slip model, and here onward we have discussed these two, we have already discussed, okay. Not the empirical correlation, we have discussed only for one case in the multi-phase flow, Locard-Martini. The several empirical correlations are there, we are not going to discuss that. Lagrangian track we have already discussed till now. Now, what we are going to discuss is the rest of the thing. So, the another set of the thing is algebraic slip model. In that algebraic slip model, as it says that it based on the slip velocity or drift velocity, we will discuss this. This has been used for the dispersed phase in a continuous phase. It means one phase should be dispersed, another phase should be continuous, then we use the algebraic slip model, and in this what we do, we solve the equation for one equation, one momentum equation, one continuity equation based on the mixture property. Okay. So, it is very similar to the homogeneous model which we have developed earlier, we were discussed earlier in the one dimensional domain. We will discuss it further here, algebraic slip model which is very similar to that, and we will discuss that how the equation will be modified in the three dimensional domain. So, what we are going to do, we are going to solve one continuity, one momentum equation, and both the continuity and momentum equation will be based on the mixture model or mixture properties, and we will also solve the volume fraction equation. So, we will see that once we will discuss the equation, we will see that volume fraction equation will additionally solve, which is different from the homogeneous model, where we will see that how the fraction of this phase is changing with the time and with the location. So, these three equations will be solved together to find the reactor behavior or vessel behavior. Then it is called two fluid model, or we popularly known as Euler-Euler model. Euler-Euler model. This is widely used model, and it is the model which you can use. I will say that this is a single model agar in a Lagrangian track, even that is difficult to implement at industrial scale. The single model as of now which we can kind of implement at an industrial scale system with a reasonable accuracy. I am quoting single model because I quoted reasonable accuracy. You can use algebraic slip model also, but the accuracy will be limiting, and the approach will be also limiting for a particular condition. But the two fluid model is widely used, and ideally you can use it for most of the conditions, and you can use this for all the scales, whatever the scales we understand, even at the industrial scale, even with the current computational power you can use that. So, what does it says that this is the Euler-Euler approach. Now, what is Euler-Euler approach? In Euler-Euler approach, we assume that both the phases which are present or all the phases which are present in the reactor or in the process vessels are continuum. It means they are a continuous fluid, and interpenetrating fluid. So, they are actually under interpenetrating continuum. Now, what do you mean by interpenetrating continuum? So, let us try to understand that. Suppose I have a bed, and I will explain it for more clarity as a gas solid. Say this is gas phase which is being injected from the bottom, there some solids are present. Now, what will happen if I take a small domain, okay, and I see that where the solids are present, where the gas are present, I will say that this is the place where only solid is present, and rest of the remaining domain only gas is present. So, this is only gas is there. But if you use the Euler-Euler approach, we lose the individual entity of the solids or individual entity of the discrete phase. Why I am saying individual entity? Because each discrete phase solid is an individual entity. Okay? So, we lose that entity and we say that this is not the solid, this is also a fluid. Now, the fluid has a property that they can mix each other, they can penetrate within each other. So, if you do that Euler-Euler simulation, what will happen? You will not get this, that there is a solid, there is a gas here, here there is, this is only solid and this is only gas. You will get in this computational domain, it will something like this, and you will say that this have actually 30% solid, say a number I am just throwing, and 70% gas. Why? Because they are interpenetrating continuum, both are continuous, both are interpenetrating, it means both will present everywhere. While in real domain, what happens? That some places only solid will be there, some places only gas will be there. They will not penetrate with each other. Like if I am sitting here, gas cannot or air cannot penetrate inside me from this body, it can go only through my nose, okay, but it cannot penetrate from my skin or cannot penetrate from my body. So, if I am sitting here, it is only me, no one else, no one else can come. But if suppose I am solving a Eulerian motion with me or kind of Eulerian equation for me or for any body, what will happen? You will see that some places if I put a domain, you will say that say 60% of me is available, 40% of gas is available. So, in that way you will see that because we are now becoming continuous fluid. Now, if we are continuous, I will be also present everywhere, gas will also be present everywhere. While if you think about this room where I am sitting right now, I am present at a particular location, okay. I am not present everywhere, but if I solve with the interpenetrating continuum with a complete domain, if I take this as a complete domain or complete room as one cell, you will find that I will be presenting everywhere because I now becomes a continuous. So, if I am continuous, I will be present in that cell, I will be present everywhere. So, in that way the particles becomes or the fluid, this discrete phase becomes interpenetrating continuum, and you solve a continuum equation for both the phases and you assume that they can interpenetrate. So, what you are going to do? You solve as many equation, okay, as many phases you are having. So, it means if you have 3 phase, you are going to solve 3 continuity equation, 3 momentum equation. If you are having 2 phase, you are going to solve 2 continuity equation for both the phases individually and 2 momentum equation for both the phases individually, and you will use the coupling to intercorrelate this motion of both the phases. So, we can solve here two-way coupling to see that how the motion of the particles, say phase 1 is affecting the phase 2, how the motion of phase 2 is affecting the phase 1. So, you can solve one-way coupling, you can solve two-way coupling, even you can solve the 3-way coupling or 4-way coupling, but for solving the 4-way coupling, you need to modify the equations, you have to include several terms and we will discuss that how to include that. So, that is the Euler-Euler approach, very widely used, and why it is very widely used? Because you are solving very few number of equation, computationally it is not very expensive. So, that is the reason it is widely used. So, like if there is a 3 phase present, you will assume that in this room all the 3 phases are present. Now, their fractions will be only different, while it may possible, say if I put a water in a glass here at this table, then maybe this what will be possibility that water is only at this location, at a particular location, I am at a particular location, air is everywhere. But if we will solve continuity kind of Euler-Euler equation, you will find all 3 of us is presenting everywhere at a different fractions. Okay. So, that is 2 fluid model. Then come to discrete element model. Now, discrete element model is very close to the Lagrangian track model. What we do? We solve here the Newton's second law of motion for each individual discrete phase. Okay. Once I say individual discrete phase, it means suppose there is a gas solid bed, there's the individual phases will be each, for each solid you will solve one Newton's second law of motion. Then we solve one continuity equation, one momentum equation for the continuous phase, say for gas phase. Okay. And then we solve the collisional part of this, that how this particle motion is going to affect the motion of particle. So, ideally DEM model can accommodate all the four-way coupling very easily, and that is the major reason that why we solve the DEM equations. Okay. So, we can have the collision equation, we can have that how the motion of fluid is going to affect the motion of the particle, how the motion of particle is going to affect the motion of the fluid, how the wake formed because of one particle movement is going to affect the motion of the other particle, how the collision of the particles is going to kind of affect the motion of each other. So, all you can solve here, and that is called by the discrete element method. What we do here, we solve one continuity and one momentum equation for the continuous phase and individual Navier-Stokes kind of the Newton's second law of motion for the discrete phase. So, if you have say 10,000 discrete phase available or 10,000 particles available, what you are going to solve? You are going to solve 10,000 Newton's second law of motion for those particles, one Navier-Stokes equation or momentum equation for the gas phase, one continuity equation for the gas phase or fluid phase. So, you are going to solve 10,002 equations. Then we also solve the collisional equation here. So, this and this difference, Lagrangian track difference is, in Lagrangian track we actually do not solve the motion of the fluid. Even if you want you can solve, but we do not take the particle collision into the account. Here we took their particle collision into the account. So, that is where it differs. So, suppose what we are going to now do, if you think about the problem, if I have a 10,000 particle in a fluidized bed, I want to use the DEM approach or DEM model. What I need to do? I have to solve 10,000 Newton's second law of motion equation to track the motion of each other particles. Then to find how the collision of between the two particles is affecting their motion, I have to solve 50,000. If I just assume that it is a two body collision and at a time only two bodies are colliding with each other, 50,000 collisional equations you have to solve, one continuity equation, one momentum equation. Okay. So, it means how many for 10,000 particles you have to solve 10,000 plus 5,000 plus 2, it means 15,002 equations. So, that make this whole approach computationally very expensive, and that is the reason that even now at industrial scale with the current computational facilities we cannot do these simulation at an industrial scale, because think about the number of equations you have to solve simultaneously, and that is why that ultimate wish which I have shown you need to be fulfilled. We should understand how to couple these equations together, or how to take the information from one set of model and use that information in the Euler simulation. And then the last one is the fully resolved and fully coupled. So, each phases are resolved individually, each phases all the way of coupling we have taken care, all the ways of interactions we are taking account. So, these all are the different modeling approach available. We will try to discuss these three modeling approach, two we have already discussed earlier. We will try to discuss these three mainly, and we will see that what equation we need to solve, what is the limitations and how to solve these equations. Okay. Now, these are the modeling approach available. If I see that, if you see that if you move from the top to the bottom, you increase your complexity, but your understanding of the physics is increased. It means, if you move from the top to the bottom, computationally you will be very expensive, or computationally you will be more expensive as you move towards the downward, but physics wise your understanding will be much better. You will be more closer to the real process condition or real process behavior, and that is the way it should move. So, this is, I will say, more physics, more expensive computationally. Once I say expensive, it is computationally expensive, okay, more complex. Okay. So, once you move from the top to the bottom. So, that is the different modeling approach available, and we will discuss about the different modeling approach in the next slide. Thank you.